back and take a look. You can absolutely do that. All righty, Chemistry 3101. Let's start off today's lecture by reviewing a little bit of how we designate R versus S on a stereo center or an asymmetric center, whatever you want to call it. And to do that, we use what are called the Kahn-Ingold-Prelog rules or the Kahn-Ingold-Prelog system. And so if I have a chiral center, and both of these molecules have a chiral center, you have to be able to designate that chiral center as being R or S. And R means that it's going to the, anyhow, R, it's an old German word, it's rectus, which means right, and S is sinister, which means to the left. Anyhow, our book doesn't even get into that, so I'm not really worried about that. But one of the things that we learned last lecture was that if you have a compound that has a chiral center, how do you recognize that compound as having a chiral center? Or how do you just recognize a chiral center? Well, you need to know that this carbon that I'm highlighting in yellow, that is a chiral center. Now, how do we know that? Because that carbon is attached to 4 different groups. Not 4 different atoms necessarily, but 4 different groups. Let me prove it to you. We can all see that we have a chlorine attached, and we know that this is a bond line structure, and therefore there is a hydrogen in the back. So let's see, we've got a chlorine here, we've got a hydrogen. Those are certainly different. If you look at the 2 other atoms, you see that we have 2 carbons, and you might think, okay, well, it's not attached to 4 different groups. Hold on. We're not just looking at the atoms, we have to look at the entire groups. And we can see that on this side, we have a methyl group. This is a methyl group. And over here, we have an ethyl group. So an ethyl group. And thus, we have 4 different groups. And therefore, what I have highlighted in yellow, the yellow carbon, if you will, is a stereocenter. And so we need to be able to designate that stereocenter as being R or S. Now, one more thing I want to mention before we get into designating this stereocenter as R or S is that if you want to draw the enantiomer of a compound, remember that an enantiomer is a non-superimposable mirror image, much like the 2 human hands that we went over last class. Now, if you want to draw the enantiomer of this compound, let's say, there's a couple of ways you could do it. You could try to draw the mirror image like this, and we could say, okay, well, these 2 compounds are mirror images of each other, thus they are enantiomers, and there's nothing wrong with that. However, there's a much simpler way to draw the enantiomer of any compound, so I'm going to erase this, and the easier way is if we have a dash, we convert it into a wedge. And thus, these 2 compounds are enantiomers of each other. Much simpler to just invert stereogenic centers rather than trying to draw the mirror image. Drawing a mirror image of a small compound like this, like these 2 compounds, not that bad. But if you try to draw the mirror image of a big compound, that can get very cumbersome. So let's get back into it. R and S. We know that these 2 compounds are enantiomers. So one more thing before we get into the designation. If this compound is R, that means that this compound, its enantiomer will be S. And if this compound is S, that means that this compound is going to be R. So as long as you are confident that 2 compounds are enantiomers of each other, if you've designated the stereochemical configuration at any stereocenter in the enantiomer, all you have to do is reverse that. So let's get into this chiral compound and let's designate the stereocenter. So here are the Kahn-Ingold-Prelog rules. We look at the 4 groups to which the chiral carbon is attached, and the first thing we want to do is prioritize them in terms of their atomic number. We have the highest priority group is the one with the highest atomic number. Well, chlorine has an atomic number of 17, and everything else is a carbon and hydrogen, and those have a lower atomic number, and thus the chlorine is going to be number 1. There's nothing that has a lower atomic number than hydrogen in the periodic table, thus hydrogen will be 4. And then if you look at this carbon and this carbon, we see that those are both carbons, so we have to look at what the carbons are attached to. So I like to make what I refer to as a laundry list of what the carbon is attached to, and you make a list of the 3 atoms that the carbon is attached to going away from the stereocenter. And thus, since this is a methyl group here, CH3, we will make the list for this carbon as saying it is attached to a hydrogen, and another hydrogen. Whereas the carbon in red, if we're going away from the stereocenter, it's attached to this carbon, this hydrogen, and this hydrogen. So if we make a laundry list for that, let's write it down. And we list those elements in order of highest to lowest atomic number. So we have carbon, hydrogen, and hydrogen. We look for the first point of difference. We see that the point of difference is here, that a carbon has a higher atomic number than a hydrogen. This is the tie breaker, so to speak. And so this group, the ethyl, is going to have the second highest priority, and the methyl will have third highest priority. Now what we do is we start at the first carbon, and we follow, going around the stereocenter, clockwise or counterclockwise, going from 1 to 2 to 3. If we do it this way, we're going clockwise, and when we're going clockwise and our lowest priority group is in the back, that means that the stereocenter is R, and thus we can write for this stereocenter, it is R. For the other compound, we can do the exact same thing. Now we know that since it's the enantiomer, it must be S. But let's go over why that is very quickly. First of all, we have a hydrogen coming out in front. And when we have a hydrogen coming out in front, here's what we do. We number our substituents, 1, 2, 3, 4. We follow, going from 1 to 2 to 3. We see that it's clockwise. So you might think, well, this one is R as well. Hold on. Now the hydrogen is coming out in front. And so if we're going clockwise, it's R. But since the hydrogen is coming out in front, it is not in back. We reverse it, and it is S. And thus, the stereochemistry at this stereocenter is S. Give me a thumbs up if you follow me on that. Or stop me if you have a question on that. All right, cool. So that's how we assign stereogenic centers using the Kohn-Ingold Prelog rule. So that's what I went over here. And it says, using handheld models can be really handy. Just some other nuances. Of course, if your lowest priority group is in front, like the second example we just looked at, you reverse the stereochemistry. What else? Another, kind of interesting rule is that, I don't recommend rotating the molecule. I just like, if the lowest priority group is in front, I reverse the stereochemical configuration like we just did. The book tells you to try other things. I recommend doing it the way that we just did it. It seems to work best for students. And there we go. So we've covered all these rules. I guess one other rule is that if you have a double bond to something, that counts as 2 single bonds. And we went over that last class. What else? Another trick. So I don't know if I went over this in detail last class, but there are some tricks that you can use. Let's say you want to draw the enantiomer of a compound, or you want to reverse its stereochemistry. If you just switch any two groups on the chiral center, just swap them, it will swap the stereochemical configuration. So if you have S, you swap two groups, you end up with R. And it could be any two groups. It doesn't have to be 1 and 4. It could be 1 and 2, 3 and 4. It doesn't matter. If you swap any two groups at a chiral center, you reverse the stereochemistry. And there's one more rule that's not in my slides, but it's mentioned in the book. I'll just put it in here. It's funny. One of my students who was preparing for the MCAT, which is the entrance exam for medical schools, he came into my office one time and he said, "Hey, Mr. Dion, did you know that if you swap two stereocenters, any two groups on a chirality center, you end up with the same stereochemical configuration?" And I said, "Yes, it's in the textbook." He said, "Oh, right. Yeah, okay." So that's another kind of funny trick. It's mentioned in the book. I didn't put it in the slides. We don't really use that one a whole lot. We went over an example last class. There's some other examples here that you could review. But let's get started on trying something new. So this is question 5.9a. Gives you a compound here. And in our book, he mentions the names of some of these interesting compounds. Like this is ephedrine. You've probably heard of, Sudafed or something like that, which is an analog of ephedrine. But anyhow, it's a decongestant. But we've got two chiral centers in this molecule. So we have this chiral center that I'm highlighting in yellow, and we have this one that I'm highlighting in green. Now I'm going to go a little faster now since we went over the rules last class and this class, but let's start with the yellow stereocenter. Just delete this. And let's see what we're attached to here. We've got an oxygen. We've got a hydrogen going in the back. We know that the oxygen must be the highest priority and the hydrogen must be lowest priority because here we have a carbon and here we have a carbon. Well, the carbon that I'm writing in blue is attached to carbon, carbon, carbon as we go away from the stereocenter, whereas this carbon is attached to nitrogen, carbon, and hydrogen. Thus, this would be our tiebreaker. Nitrogen has a higher atomic number than carbon, and thus this would be our second highest priority group. This would be third. We're going 1 to 2 to 3, which is clockwise. The lowest priority group is in the back, and thus the stereochemistry at this stereocenter is R. So let's erase some of this spinach so that we can kind of see what's going on. And there we go. Let me just leave it like this. So this is our stereocenter here. Let's look at the next stereocenter. I'll erase the rest of this. And let's take a peek at this one. So we have the stereocenter I'm highlighting in green. Excuse me. But what's it attached to? We've got a nitrogen, we've got a carbon, we've got another carbon over here, and we have a hydrogen going in the back. So let's write that hydrogen that's going in the back. We know it's going to have the lowest priority. The nitrogen will have the highest priority. If we look at this carbon, it's attached to 3 hydrogen atoms, whereas this carbon is attached to an oxygen, a carbon, and a hydrogen. This is the tiebreaker. Thus, this carbon is the second highest priority. This one is third. So we are going from 1 to 2 to 3, like this, which is counterclockwise. Our lowest priority group is in the back, and therefore the stereochemistry here is S. So let's scribble off or remove some of this stuff here for clarity's sake, and we can say that this is S. Everybody with me on that one? Any questions about that one? Again, this is question 5.9a. The entire solution is worked out in the textbook. Let's try one more, and then we're going to get into something new. So here's another compound. We've got a couple of stereocenters here. This is an anti-tumor agent that's isolated from a marine organism. It's called halomon. Anyhow, so we've got a couple of stereocenters in here, and let's see if we can designate their configuration. So we'll start with the one on the left. Start here. And let's see, we've got a chlorine, we've got a carbon, we've got a carbon, and we've got another carbon. So obviously chlorine has the highest, atomic number of all these. So we'll give the chlorine number 1. And if we look at this carbon here, this one is attached to a bromine and 2 hydrogens. Well, there's nothing that's got a higher atomic number than a bromine in here. And thus this must be the second highest priority group. Now let's take a look at the 2 others. I'll put this one in blue. Like that. So the one that I have in red is attached to a chlorine, a carbon, and a carbon, whereas the one that's in blue is attached to a carbon, a hydrogen, and a hydrogen. This would be my tiebreaker. Chlorine has a higher atomic number than carbon, and thus this would be my second highest priority group. This would be, that would be my third highest priority group, and this one would be fourth. So I'm going from 1 to 2 to 3 like this, but you're like, well, hold on, Mr. Dion, where's my lowest priority group? My lowest priority group, number 4, is not in the back, right? It's in the plane. It's going like this. So what I want you to do is something a little bit different. Now what we're going to do is we're going to imagine that we're staring at the molecule this way, okay? I want you to imagine you're looking down this carbon-carbon bond, and that way the lowest priority group would be behind you, right? This carbon would be in the back. This carbon would be in the front. So what would you see with your eyeball if you were looking down that bond that I have highlighted in yellow? I'm just going to kind of draw a quick version of a Newman projection, and what you would see is you would see the chlorine coming up and to the right. You would see the methylene with the bromine on it going up and to the left, and you would have this carbon that has the double bond and the chlorine going down like this. Okay, this is what you would see. I'm looking at this carbon right here, the one that I have the big red dot on. And so we're going from 1 to 2 to 3 like this. And so you can see that that is S because we're going counterclockwise. So we have to kind of manipulate that molecule in our mind a little bit. So our stereochemistry at this stereocenter is S. So I'll just scribble that in there as S. Oh boy, I don't have a lot of room to look at the next stereocenter, so why don't I just redraw the molecule quickly? Just bear with me here as I redraw the entire thing. So we have our bromine, so this is our second stereocenter. up here, and then we have a chlorine over here. What else am I missing? Got this, and then I have this chiral center that we just designated as being S. There we go. Okay, so we know that this one is S, and now let's try the next one. So this one right here, let's take a look. Well, bromine obviously has the highest atomic number of all. We have our hydrogen coming out in front. That has the lowest atomic number. Then if we look at this carbon, it's attached to chlorine, carbon, carbon. And this carbon is attached to carbon, hydrogen, hydrogen. This is my tiebreaker. So my second highest priority group is going to be this one here. My third highest priority will be this one here. We go from 1 to 2 to 3. We're going counterclockwise, which would be S, but we reverse it because the lowest priority group, excuse me, is coming out in front, and therefore this stereocenter is R. There we go. So we have S for the stereocenter on the left, and we have R for the stereocenter on the right. There you go. You can imagine that this is a very important concept for organic chemists because we're always looking at chiral molecules, not every day, but a lot of the time in these classes. And therefore, it's crucial that students master the Ingold Prelog rules. I mean, how are you going to do it for real? Can it be mastered by watching me solve problems on YouTube or in class? The answer is, I would say no. Is there something to be learned from that and something to be gained from that? Of course, but you're going to have to go into the book, look at the practice problems where it says just designate the stereocenters as R and S, and just master that, that concept. All right, so let's move on and get into something new. We're still in section 5.3. And now we're going to discuss what's called optical activity. Check this out. You have to really think about this, but if you have two enantiomers, so let's say we have these two compounds, we know that R carbon and S carbon are enantiomers because they only have one stereocenter. You go from a wedge to a dash, and you've drawn the enantiomer. Okay, so we've got two enantiomers. How would you distinguish between these two enantiomers? How would you tell them apart? If I gave you, they both have a melting point of 25 degrees Celsius, so they're probably, kind of like almost a semi-solid at room temperature. But anyhow, let's say you had the compound, and let's imagine it's two white solids. Like, how would you tell the difference between the two? Can you use melting points and boiling points and densities? No, you can't. They both have the same melting points and the same boiling points. They would have the same densities. Any kind of physical property is going to be identical. Why would those be identical? Because if you think about what physical properties, where they come from, where does melting point come from? Where does boiling point come from? It comes from intermolecular forces, the way two molecules interact with each other. So you can imagine that if I have a second molecule of our carbon, if I just pencil it in here quickly, I'm not going to have enough space here, but let's say I have a second molecule of this. If I have two molecules of this, they're going to pack on top of each other the same way as if I had its enantiomer. Okay, if I drew the enantiomer, it's going to pack the same way with other molecules of the other enantiomer. So since the interactions between the two enantiomers, if you have, a bunch of one enantiomer or a bunch of the other, they're going to interact in the same way, and thus they're going to have the same physical properties. Let's imagine if you were to run an infrared spectrum on both of these compounds. What would you see? You would see the carbonyl stretch. You would see the sp2 hybridized carbon-hydrogen bonds here. Okay, let's say could you distinguish between them using IR? The answer is no. Could you distinguish between them using mass spec? No, they're going to have the same mass spec because it's the same connectivity. They're going to fragment in the exact same way. And so how do we distinguish between them? Well, here we go. Here's the answer. You have two enantiomers. They only differ in two things. Number one, how they interact with other chiral compounds. That we're not going to be all that concerned with in Chemistry 3101. But the way that we're going to discuss how you would determine, which enantiomer is which is by their optical activity. Okay, so optical activity means how the compounds interact with light. Before we can get into that, we need to do a little bit of background on what optical activity is. So we know that if we have light emanating from some kind of source, so let's say we have a light source here, okay, let's just imagine that this is a light bulb, okay? Like Mr. Dion is not much of an artiste, but anyhow, here's our light bulb. Well, if you have a light bulb at home, you know that light is emanating from that light bulb in all directions, okay? We know that light travels in waves. Light is electromagnetic radiation, and so it has an electric field component and a magnetic field component. But we know that those waves move in specific planes. Now, I don't have the planes in here, but we know that light travels in all these different planes. Okay, it can travel in this plane, it can travel in this plane, etc., etc. But what happens is if we take light and the fact that it travels in a plane is called its polarization. So you have all these different polarizations. If you pass light through what's called a polarizing filter, so this is a polarizing filter right here and right here. When you shine light that has all these different polarizations, if you put it through a polarizing filter that only allows one of the polarizations to pass through, then what you see on the other end is only the light with that specific orientation or polarization. So it's just this one here. And we call that plane polarized light. So here we have the first filter, the first polarizing filter. We only allow light with this polarization to pass through it. Then if we have a second filter and we have it aligned in the same way as the first filter, it's going to continue to allow this polarized light to pass through and reach your eyeball. Well, if you take the second polarizing filter and if you were to rotate it 90 degrees like this, well, your light has this polarization, but the filter is turned 90 degrees to it, and thus the light cannot pass through it. It will not reach your eyeball, won't get through. Now, has anybody here, and I'll just ask you, it's hard to do a show of hands on Microsoft Teams, but has anybody here ever seen an expensive pair of sunglasses in a store that has a polarizing filter hanging on them, like a little tag hanging on polarized sunglasses? Sometimes if you see Coco Chanel sunglasses or Oakley's or something, expensive sunglasses that are polarized, they'll have a little hang tag on them. And the way that the consumer knows that the sunglasses are actually polarized is they'll take the second polarizing filter and you can rotate it next to the pair of glasses, next to the lens. And if you rotate it one way, it will allow light to pass through it. And if you rotate it 90 degrees, the light will be blocked. I got no shows of hands. Has nobody seen this before? Nobody's seen, expensive sunglasses? Okay, one person maybe. Okay. One person's a high roller, maybe, shopping for expensive sunglasses. But the bottom line is that you need to understand what plane polarized light is. So light, when we pass it through a polarizing filter. And here's what's so cool. This is why plane polarized light is so important to organic chemists, is when plane polarized light is passed through a sample of a chiral compound. The chiral compound, the chiral compound will actually rotate the plane polarized light. It'll twist it to one direction or the other. And so compounds like a chiral compound that can rotate plane polarized light, we say it's optically active. Okay, we say that it can rotate plane polarized light. Here's another diagram that'll hopefully clear things up for you. Okay, so look, you have your light source. Now, normally we use the D line of a sodium lamp. So we use a sodium lamp and we use the D line, which has a wavelength of, I think, 589 nanometers. I don't know if it's in my slides or the book or whatever, but anyhow. So you have this specific wavelength of sodium. The sodium lamp is going to emanate light waves with all these different polarizations. You pass it through a polarizing filter, so you end up with your plane polarized light. That's this light right here. That's plane polarized. Now what you do is you take your organic compound in a solution, and it could be in an organic solvent like dichloromethane or something. But anyhow, you have a solution of your organic compound, and if the compound is chiral, what it's going to do is it's going to twist, it's going to rotate the plane polarized light. So you can see here, it's twisting in this direction. It's moving it over here, then more and more, until it's kind of ending up perpendicular to the way that it started now. So how would you view it on the other end? What you do is you have a second polarizing filter on the other end, and to figure out how much the polarized light was rotated, or what's the word I'm looking for, was had its angle changed, or how much it was rotated, I guess, from its initial angle. You are going to adjust the polarizing filter down here so that you can see light. So you can see that the person had to rotate it 90 degrees, and then once they rotated it 90 degrees, then the light was able to pass through and the person was able to see it. So you keep adjusting the second polarizing filter until you can see light coming through it. Then you just look at the scale and you say, well, I rotated it 90 degrees, so done. I know that this chiral compound can rotate light 90 degrees. Now here, are you ready? Here's the truth bomb. If you have one enantiomer and it rotates plane polarized light, let's just pick a number, positive, 50 degrees, the enantiomer is going to rotate the plane polarized light in an equal amount, but the opposite direction. So it would be negative 50 degrees. And that is the main take-home message. Check it out. Enantiomers are going to rotate the plane of light to equal degrees, but in opposite directions. So let's just say, for example, if you have enantiomer, let's say you have enantiomer A and it rotates plane polarized light at positive 88 degrees, that means that enantiomer B is going to rotate plane polarized light at negative 88 degrees. And these are just numbers I'm pulling out of a hat. Now, the amount to which the light sample, or the degree to which the light is rotated, depends on concentration, path length, and our textbook goes into all kinds of examples of calculations of how you calculate specific rotation and how it's affected by temperature, how it's affected by concentration, how it's affected by the path length, how it's affected by wavelength. The bottom line is you don't need to worry about any of that, okay? I'm not going to ask you any questions about calculating optical activity. I know there are questions in our textbook that deal with that, but if you look at the problems that I selected from Chapter 5, you'll notice I picked none of those problems. So you need to focus on the problems that I selected. And the main thing that you need to know is this. If you have one enantiomer, let's imagine you have R2 bromobutane. It has an optical rotation of negative 23.1 degrees. The enantiomer S2 bromobutane is going to rotate plane polarized light by positive 21 degrees. So just a little bit about these numbers here. So alpha, that just stands for the optical rotation. The 20, that represents the temperature. So this is temperature. And then D means the wavelength of the light. And I told you it was the D line of sodium. Don't worry about that. I'm not going to bring that up really in the quiz or anything and ask you about it. It won't show up on the final exam either. The bottom line is that you need to know that enantiomers are going to rotate plane polarized light by equal amounts in opposite directions. Now, the whole positive and negative, what does that mean? You saw positive and you saw negative. Well, you can probably guess that positive and negative has something to do with the sign, or sorry, the direction to which the plane polarized light is rotated. If it's positive, it means it's rotated in a clockwise direction. And if it's negative, it's rotated in a counterclockwise direction. All right. So a couple more things. The positive rotation, again, which is clockwise, we call that dextrorotatory. And the negative direction, we call that levorotatory, and that's counterclockwise. But here's the thing. Two more major points or truth bombs that I need to drop on you. Number one is, let's take a look at this compound here. So this is an amino acid. Excuse me. And it says here that this compound has the S configuration. Let's double check. If we look at this chiral center, we see the hydrogen is going in the back like this. So it has the lowest priority. Nitrogen is 1, hydrogen is 4. This is number 2, this is number 3. So we go from 1 to 2 to 3. That's going counterclockwise. So yeah, they're right. This is S. Okay, well, check this out. It says the optical rotation of this compound, which has one stereocenter, that is S, it's levorotatory or negative at 20 degrees Celsius, but at 100 degrees Celsius, it's positive. And thus, there's no correlation, or sorry, what should I say? The optical rotation, whether it's positive or negative, is temperature dependent. But the biggest truth bomb is this one here. Students always want to connect R and S with positive and negative. They say, well, if it's S, it must be negative. If it's R, it must be positive, one or the other. The bottom line is there's no correlation between the two. Just because a compound is R, you have no idea whether it's going to rotate the plane polarized light in the dextrorotatory or the levorotatory direction. You have to do the experiment. You've got to measure it yourself. End of story. You can't, no scientist can look at a compound and say, you know, I think this one is going to be R, people. There's no way to determine that. You have to measure it yourself. That is it. It's the only way. So again, the magnitude, the direction of optical rotation cannot be predicted. Nobody is out there who's smart enough to say, yeah, I think it's this and things that. The only thing you got is you've got to do the experiment and measure it. However, if we have a racemic mixture, the optical rotation is going to be 0 degrees. Now, if you're wondering, what's a racemic mixture? You know how we have one enantiomer and then we have the other enantiomer? So let's imagine we had these two compounds. So if I draw this compound, and then if I draw its enantiomer, like this, okay, and this is just, oops, that's not its enantiomer. If I draw its enantiomer, and I'm just coming up with a hypothetical example here. I don't know what the optical rotation of either of these molecules is, but we know that these two compounds are enantiomers. These are enantiomers of each other. Okay, so let's just imagine that this compound rotates plane polarized light negative 51 degrees. That means that this compound is going to rotate plane polarized light positive 51 degrees. So a racemic mixture is a 50-50 mixture of two enantiomers. So if I have this compound and this compound in a 1-to-1 ratio, it means half of the sample is going to rotate plane polarized light negative 51, but the other half is going to rotate it positive 51. What happens if you take negative 51 degrees and then you add positive 51 degrees? You get 0 degrees. And that is why when you have a racemic mixture, a 50-50 mixture of two enantiomers, you get no rotation. It doesn't do anything. Give me a thumbs up if you follow me on that concept, or stop me if you have a question. Is everybody with me on that? Yeah, you mix two things that are equal and opposite, you end up with nothing, no rotation. And we can have a situation where you have one enantiomer in excess over the other, and that's going to end up in an optical rotation, but it's usually going to be less, or it will be less than if you had the pure enantiomer by itself. We call that enantiomeric excess. I'm not going to ask you any questions about enantiomeric excess. Okay, so don't worry about enantiomeric excess. I'm not going to ask. So I'll even write it down here so you have proof. Not going to ask any calculations. Again, if you're sitting there wondering, students are always wondering what's going to be on the quiz. Are you going to try to trick me? Is there going to be something that you didn't talk about and you're going to surprise me and be like, you should have looked at it in the textbook? No. What you want to do is you go into Canvas, you go into the Chapter 5 module, and you look at the suggested practice problems. And when you open that up, you'll notice there's some numbers that I skip in there. It doesn't go from 1 to 29. You see there's a bunch of numbers that I skipped in there. What that means is you don't have to worry about the content that's in those questions, okay? Stick to the questions that I assigned. Those are the ones you want to worry about. And you'll notice that any question in the book that deals with calculations of enantiomeric excess and that kind of stuff, I skipped them. So don't worry about them. If you want to go back on your own time and look at those, be my guest. This is the land of the free. You can totally do that. But here is the summary of this section of what you need to know, okay? You need to understand what plane polarized light is. You need to understand that when you pass polarized light through a solution of a chiral molecule, it's going to rotate that plane polarized light. You need to understand that two enantiomers are going to rotate plane polarized light in equal and opposite directions. You will not have to calculate specific rotations or enantiomeric excess, but you should know what it means when I say something is optically pure. It means you have a pure enantiomer. You should understand what enantiomeric excess means. It just means that one enantiomer is present in a higher percentage than the other. And then you should understand what a racemic mixture is. And a racemic mixture is nothing more than a 50-50 or 1-to-1 ratio, 50-50 mixture of two enantiomers. That is what you need to know, my friends. That's it. So again, don't be stressed about, oh no, he's going to ask me a bunch of calculations. I'm going to need to bring in a mainframe computer. Don't worry about that. Not part of the class. Any questions about those concepts before we move on and get into what are called diastereomers? So something a little bit different. We're going to talk about diastereomers. No? Okay. Well, let's get into it here. And you know what? First, let's go over this slide together. Then I'll give you a couple of examples, maybe using some models that I have here on my desk. Section 5.5 deals with enantiomers and diastereomers. So if we look at categories of isomers, where we started the chapter was here. We said, okay, you can have isomers, you can have constitutional isomers. That's compounds that have different connectivities. I gave you ethanol and dimethyl ether as my example. And then, you know, this is really the focus of this chapter is stereoisomers, obviously. And we said that two stereoisomers are compounds that are non-superimposable. We started out with using the example, I think, of two human hands. Then we used the example of the pairs of John Lennon glasses with the lens poked out, and then its mirror image. We said those are non-superimposable, but they're mirror images. Then I held up some models to you. And it says here that if you have non-superimposable mirror images, we call those enantiomers. Whereas if we have non-superimposable molecules, but they're not mirror images, then they fall under the umbrella of a new type of stereoisomer, which is a diastereomer. So let's take a look at a model here. So let me go over to the old camera. So I'm sorry you have to look at my face on a Wednesday morning, but here's what we got. We said, oops, let me go back to my camera. We said if you have two molecules that are mirror images, like these two molecules here, you can see that these are mirror images of each other. They are not superimposable though. So we said non-superimposable mirror images, these must be two enantiomers of each other. And we said, well, the way you know that this carbon is chiral is because it's attached to 4 different groups. You make its mirror image, they're non-superimposable, and so you have a pair of enantiomers. If you're wondering, you know, what's an example of a diastereomer? Well, the simplest type of diastereomer that I could give you would be a transalkene that we talked about last class, and a cisalkene. Remember these? We looked at these last class. We said that these two compounds are stereoisomers of each other, right? I can't overlap one on top of the other. Are you with me on that? That you can't overlap the cis and the trans? Obviously, you can see that the white and the yellow or light green sphere, neon, whatever you want to call it, it doesn't line up. And, you know, if you're wondering, you know, why don't you just rotate the molecule? Well, when you have a pi bond, you can't rotate the molecule. Now, here's the definition. On that slide, it said diastereomers were stereoisomers, so non-superimposable, but they weren't mirror images. These two compounds are not mirror images of each other. You can see that there's no reflection between the two. Some points are mirror images, but these 2 points aren't mirror images. So these are not mirror images, and they're not superimposable. Therefore, cis and trans isomers would be an example of diastereomers. Now, there are other examples that we're going to look at, but that's actually the simplest type of diastereomer that I can show you. So is everybody with me on a diastereomer? Or at least the definition of it? Cool. Yeah, pretty neat, huh? Diastereomers and enantiomers. So again, enantiomers, stereoisomers that are exactly mirror images, whereas diastereomers, they're stereoisomers, but they're not mirror images. So again, the simplest type of diastereomers that I could show you is what I just held up, cis and trans isomers. If I take this molecule and try to plop it on top of here, I can't do that. So they're non-superimposable. But if I look at the mirror you know, if I draw a mirror plane between the two, well, they're definitely not a reflection of each other. They're not mirror images. And so, again, they're diastereomers. Now, remember that enantiomers have identical physical properties. The example that I showed you a few slides ago was R and S carbone. Well, enantiomers do have identical physical properties, but diastereomers will have different physical properties. These are going to have, these two compounds will have different melting points, different boiling points, different densities. Why is that? Because if you had, let's imagine you had 100 of these molecules, cis-2-butene, they're going to stack together differently than if you had 100 of these molecules. And where do physical properties come from? They come from intermolecular forces, the way that molecules interact with each other. And since we have different intermolecular forces between diastereomers, we have different physical properties. Are you ready? Let's take a look at if we had a cyclohexane molecule that has 3 substituents. Okay, so 3 substituents. Here we have a hydroxyl, we have a methyl, and a chlorine. Now, before you get in, don't get intimidated at this slide. I'm going to go over it the simplest possible way I can. Are you ready? Let's just look at 2 of the molecules. What's the relationship between these 2 molecules? If I put these 2 molecules here, could anybody tell me, how would you describe the relationship between these 2? Would these be enantiomers or diastereomers, do you think, based on what you've learned up to now? Anybody have a thought about that? Would these be enantiomers or diastereomers? Keep in mind, nobody has a thought? Okay. Look, if we examine these 2 molecules, notice this wedge has been converted to a dash, this wedge has been converted to a dash, and this wedge has been converted to a dash. Exactly. Right, Tracy? Every single dash and wedge is switched. Therefore, these 2 compounds are enantiomers of each other. Simple as that. These 2 are enantiomers, enantiomers. What's another way you could know that without even looking at the molecule? We go from 1R to 1S. We go from 2R to 2S. And we go from 3S to 3R. Again, we switched every single stereocenter from R to S or S to R. Thus, these 2 compounds are enantiomers. And if you look at any of these green boxes in here, what each one of these green boxes represents is a pair of enantiomers. These 2 compounds are enantiomers. This wedge is a dash. This wedge is a dash. This dash is a wedge. Ergo, these 2 compounds are enantiomers. R became S. R became S, and R became S. Therefore, these compounds are enantiomers. We see the exact same thing with these 2 compounds, and we see the same thing with these 2 compounds. And thus, in each one of the green boxes, we have a pair of enantiomers. All right, but we know that in each one of these green boxes, we have a pair of enantiomers. But now I want to look at a different relationship. Let's pick the first molecule in the top left-hand corner, this compound, and what if we were to compare it to this compound? What would the relationship be between the compound in the yellow circle and the compound in the red circle? Are they enantiomers? No. You see that this wedge is still a wedge. You see that this wedge is still a wedge. But this wedge, this one going down, is now a dash. Are they identical? No. Are they enantiomers? No. But are they stereoisomers? Yes. They have the same connectivity, but they have a different arrangement of the atoms in space. Thus, they are diastereomers. And so the conclusion is that the compound in the yellow circle is a diastereomer of this compound, son of a. It is the diastereomer of every single other compound in here. So the compound in the yellow box has one enantiomer, one non-superimposable mirror image, and it has 6 diastereomers. Give me a thumbs up if you follow me on that idea. Remember, diastereomers are stereoisomers that aren't enantiomers. Okay, so the same rationale would apply to every single molecule in here. You could pick any molecule on this page. Let's just pick this one at random. This compound has one enantiomer, this guy right here, but it has 6 diastereomers. 6 of them. All right, so now that we know the relationship between enantiomers and diastereomers, let's move on and look at a compound that has even more stereocenters. You know, you might have been wondering, is there a way to predict how many stereoisomers I can have? There is. There's a quick formula that we can use to determine the maximum number of stereoisomers. What you do is you take 2 to the power of n, where n is the number of chirality centers, and that tells you the maximum number of stereocenters you can have. So if we go back to this slide, we see that all of these compounds have 1, 2, 3 stereocenters, each one of them. So if we have 2 to the power of n, where n is equal to 3, 2 to the power of 3 is 2 times 2, which is 4, times 2, which gives you 8. That means there's a maximum number of 8 stereoisomers. Is that what we see? Absolutely. Well, let's take a look at another molecule. What about cholesterol? What about cholesterol? How many possible stereoisomers would there be for cholesterol? Well, it might take you a second, and hopefully you've taken the time to go through the slides before coming to class, and you've tried this, but we have a stereocenter here. We have another one here, 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 and here. So that means we have 1, 2, 3, 4, 5, 6, 7, 8 stereoisomers. So the maximum number of stereoisomers for cholesterol is 2 to the power of 8, which is 256, I believe. If we take 2 to the power of 8, we get 256. So that means that cholesterol has 256 possible stereoisomers. Stereoisomers. Pretty remarkable that the human body always synthesizes this one stereoisomer. And so cholesterol as a molecule, think about it. If there's a total of 256 possible stereoisomers, let me ask you, how many enantiomers would cholesterol have? How many enantiomers could cholesterol have? Could anybody answer that? How many enantiomers for cholesterol? Exactly. There's only one possible enantiomer. So cholesterol has one enantiomer. Therefore, it will have 254 diastereomers. Right? You've got one cholesterol, one enantiomer, so that's 2. Everything left over is going to be a diastereomer. And again, I think it's pretty remarkable that the human body always ends up synthesizing the correct stereoisomer. Pretty neat. All right, excuse me. Let's try a problem. It says here, identify whether each of the following compounds are enantiomers or diastereomers. So let's start with this 5.19a. Anybody have a thought about these two compounds? Would these be enantiomers or diastereomers? I bet you my students know the answer. Yeah, that's right. Anybody else have a thought? Yeah. I see Kiana, Angel, Tracy, they all say they're enantiomers. They are all correct. We see that this wedge is becoming a dash, and that this dash is becoming a wedge. Therefore, these are enantiomers. Enantiomers. Like that. What about the next one? What about B? Anybody have a thought about B? Yeah, absolutely. Absolutely. Everybody who's typing in diastereomers is 100% correct. We see that this wedge is becoming a dash, but this wedge here is staying a wedge. And so they're not enantiomers, but they are stereoisomers because they have the same connectivity, but a different arrangement of atoms in space. Therefore, these are, excuse me, Diastereomers. That's right. And what about the last one? This one is trickier, definitely tougher, right? We're not sure. We've got a couple of possibilities. Um, there's two possibilities. Let me show you what you would do with C, because hopefully you can see that this stereo center here hasn't been changed. But kind of the question is kind of like, what about this one? I mean, here the chlorine's pointing down, but here it's pointing up. Damn it, I can't compare these two things directly. So you have two options. Option number one would be to rotate this bond and put this methyl in the same plane as this one and then see where the chlorine is. So that's one option. Let's try that first. And this is where handheld models can come in really handy. No, no pun intended. So if we have the hydrogen going in the back of the page like this, and here we have the hydrogen going in the back of the page like this, what you would do is you would rotate, why don't we rotate this bond, rotate it kind of like this so that the methyl goes up here. So if I do that, I'm rotating that bond 120 degrees. And so what I end up with will be this. So let's see, this hydroxyl is going to be here. So what happens is the methyl is going to go up into here. The hydrogen is going to come out in the front, and the chlorine is going to be in the back, right? You see how everything's kind of swapping places. And so the chlorine will be in the back like this. And so we can see that this, son of a gun. So we can see that this wedge is still a wedge, but this wedge became a dash. So these are diastereomers. That's one way of solving the problem. So these two compounds are, in fact, diastereomers. I'm not going to go over solving the entire thing right now in terms of determining the stereochemistry of each stereocenter. I'll let you do that on your own time to get a little bit more practice. But the other option is to do this, is just assign the stereochemistry of every chiral center. And when you do that, you find that this one is R, this one is R, whereas over here, this one is R and this one is S. And since we have R and R and S, since one of them got switched, then they must be diastereomers. But you could try that on your own time. All right, give me a thumbs up if you follow me on diastereomers and enantiomers. This question a little bit trickier because you got to rotate a bond. It's not a trick question. I didn't say that. It's tricky, okay? There's nothing in organic chemistry that's simple. Like one of my colleagues says, if it was simple, everybody off the street would be able to do it. And that is certainly not true when we're talking about organic chemistry. Why don't we cover another section here before we take a break, and that deals with symmetry and chirality. One thing I find my students are very good at, and I'm talking about you guys, one thing I find students are great at is recognizing points of symmetry in molecules. I find that students are very good at, saying, okay, well, if I drew a line, just imagine you had this compound. If I draw a line down here, you can see that these two sides are identical, right? There's a mirror plane in this molecule. Whereas if you draw a mirror plane here, you can see that this compound does not have, reflectional symmetry. There's no mirror plane. Do you follow me on that? Or do you have a question about that? I'm kind of getting ahead of myself a tiny bit. But does everybody see what I'm saying? That this compound does have a mirror plane. There's a plane of reflection here, whereas there isn't in this molecule. Okay, cool. So let's get into it here. Okay, how do we know we've got a chiral compound? Well, if you have a compound that's got one chirality center, it's chiral, no questions asked. So going back to, again, there's no such thing as a simple example, but just going back to a molecule like this, so this would be what, R2-bromobutane. You've got one chiral center. This compound is chiral. There's no arguing. There's no debating. There's no thought required. It's got one chiral center. It is chiral. Now, you've heard me say this probably every lecture since we started this class, to the point where I'm sure you're sick of hearing it. But I just want you to be aware that, never think that you're alone in organic chemistry. All students, tend to get to a point where they feel like organic chemistry is all about learning a bunch of rules and then the exceptions to those rules. So here's an interesting scenario. If you've got more than one chirality center, so if you've got two or more chirality centers, the compound may not be chiral. Okay, so just wrap your head around that for a second. You've got more than one chiral center, but the compound isn't chiral. Well, if you're like, well, hold on, isn't the definition, if it's got a chiral center, doesn't that mean it's chiral? No, the definition of a molecule being chiral, the molecule being chiral, is that it can rotate plane polarized light. Let me repeat that. A chiral center is a carbon that has 4 different groups attached to it. However, you can have a molecule that's got chiral centers in it, but the molecule itself will not rotate plane polarized light. Check out these two compounds that we have here. We've got trans 1,2-dimethyl cyclohexane, and we've got cis 1,2-dimethyl cyclohexane. Well, these two compounds are stereoisomers, are they not? You could even practice drawing the 2D structure here. So if we were to draw this one, you would see that you have one methyl group going up, you have the other methyl group going down. Here we have both methyl groups pointing up like this. We have cis and trans. Okay. Well, I want you to understand that this is a chiral center, this is a chiral center, this is a chiral center, this is a chiral center. Those are all chiral centers. What's a chiral center? It's a carbon that's attached to 4 different groups. Now, I'm not going to go over all 4 of these. Let's go over 2 of them. If I look at the carbon that's highlighted in yellow, is it attached to 4 different groups? Yes. You've got the methyl group. You've got a hydrogen pointing straight down. You have this carbon that's got a methyl group on it. And then you have a CH2 or a methylene over here. Those are 4 different groups. That is a chiral carbon, and the same rationale applies over here. So that molecule has 2 chiral centers. There's no debating that, and I hope you follow me on that. Let's go over to the other molecule, the carbon in blue. Let's do that one. That carbon is attached to a methyl group, a hydrogen that's pointing down, a carbon with a methyl group on it, and a CH2. That is a chiral center. Same rationale, isn't it? But every carbon that I have highlighted in these 2 molecules, the red, the yellow, the blue, the green, those are all chiral carbons. But here's what's interesting. One of these compounds is chiral and one of them isn't. Now hold on, listen to what I said very carefully. They all have chirality centers. However, sometimes you can have more than one chirality center and the compound may not be chiral. When does that occur? This is what I skipped until now. When it has a plane of symmetry. Could anybody tell me which one of these molecules has a plane of symmetry? A line through it? Would it be the trans or the cis? Which one has a plane of symmetry? Plane of symmetry in it. Like a mirror plane running through the molecule. Would it be the trans or the cis? Absolutely. Right? Yeah. Yes, it's the cis, right? You can see that there's a mirror plane going through this molecule right here. Look, if we look at the bottom line structure, wouldn't you agree that there's a mirror plane? There's a reflection on both sides here? Yes, absolutely. Whereas in this molecule, this is not a mirror plane. The reflection doesn't work. Same thing here. There is no reflection. So the molecule that has a mirror plane, even though it has 2 chiral centers, it's not a chiral molecule. Now, if you're going, well, why the heck would that be? Why would that be? Well, hold on. Check this out. This is why. What did we say? If you had 2 chiral centers, but they're mirror images of each other, that means they have opposite stereochemistries, don't they? One is R, one is S. What happens if you have a 50-50 mixture of 2 stereocenters? But now they just happen to be trapped in the same compound. Remember, one is going to rotate plane polarized light in one direction to a certain amount, And the other stereocenter is going to rotate plane polarized light in the same amount, but the opposite direction. And they cancel each other out. So it's just two chiral centers in the same molecule, but they're canceling each other out, so to speak. And so we end up with something that isn't chiral. So going back to this whole idea, the cis 1,2 dimethyl cyclohexane has a plane of symmetry. It's shown here. And so this molecule is actually achiral. And we have a name for this kind of compound. We call it a meso compound. Not spelled the same as miso soup, but it's a meso compound. So a meso compound is a compound that has two or more chirality centers, but it's got a plane of symmetry running through the molecule. So the two chiral centers cancel each other out, so to speak. By definition, when a compound is identical to its mirror image, the compound is not chiral. It is achiral. So if we have a compound that's identical to its mirror image, it's not chiral. And with a meso compound, if you draw its mirror image, it's identical. So it's definitely not chiral. There we go. So that deals with meso compounds. Now, you remember that formula I taught you a few minutes ago, 2 to the power of n? Well, you've got to take that formula with a grain of salt. And here is why. If a compound has a plane of symmetry, it's achiral. Good enough. So when you have a meso compound, you will have less than the predicted number of stereoisomers based on this formula. Let me show you what I mean. If you're like, I'm not following you, hold on. Let's take a look at just this compound. Okay, so we have trans 1,2 hydroxy cyclohexane. Okay, we have a chiral center here and we have a chiral center here. There's no debating that. We reverse them and we end up with a pair of enantiomers. But if you have two chiral centers and you use that formula, you might say 2 to the power of 2 equals 4. Therefore, I'm going to have 4 stereoisomers. However, if you draw this molecule, the cis, and then you reverse both of those stereogenic centers, hopefully you can see that if you rotate this 180 degrees, you end up with the exact same thing. And so because we end up with a meso compound, we actually end up with 4. You have to remove one, and we actually only end up with 3 possible stereoisomers in this particular case. If you go in our textbook and look at the practice problems that I handpicked, you will find a few examples that cover this exact rule where it says, how many possible stereoisomers could you have? Could you have meso compounds? And one such problem is this compound, or this question right here, 5.24. It says draw all of the possible stereoisomers that you could have for these compounds, and every stereoisomer should only be drawn once. So what I want you to do, we're going to take a short break, and I want you to try to draw all the possible stereoisomers of this compound, all the possible stereoisomers of this compound, and see if you can identify if there are any meso compounds. There could be, maybe not, but since it's in this section, there probably will be. But that's what I would like you to try. And then after we come back from the break, we'll go over the problem, and then we're going to talk about Fischer projection. So if you've ever studied carbohydrates, glucose, and fructose in biology, you may have seen a Fischer projection, which looks like a Fischer projection of glucose, kind of looks like this. This isn't D-glucose, this is L-glucose. But anyhow, you get the idea. We're going to come back to that in a second. So again, after our break, the first thing we're going to do is tackle this problem. So give it a try.